To understand how we can generalize counting sort, I have a question for you. Let's suppose that instead of numbers, we have card suits. Here I have clubs, spades, hearts, diamonds, in this order. So that clubs is considered smallest and diamonds is considered largest. Just some arbitrary ordering that I picked. Okay. So, question for you. If I have the following folks, Lauren, Delbert, Glazer, etc., with this as their key, their card suit, what will be the index of the first heart? Okay. So use your intuition, do whatever needs to happen. Pause the video, figure out where the first heart will go, and if you'd like, also figure out which heart will be first. So, to solve this problem, to know where the first heart goes, I'm going to observe that we have so many clubs, so many spades, and then heart will be next. So in particular, we have 1, 2, 3, 4, 5 total items, which are less than the first heart, and so the first heart will go in this position, position 5, and it will be ultimately Delbert who ends up in this position. So that's the key insight that allows us to generalize to non-unique, non-numerical keys. So the basic idea behind counting sort ultimately is you count the number of occurrences of each item, and then you iterate through the original list using the count array to decide where to put everything. Okay. So let's see a little demo here, and we're just going to step through the whole process of counting sorting all these items. And this is one particular way you can implement it. There's lots and lots of implementations, but this is the way that I've chosen to implement it because it's the simplest. All right. So again, we have clubs, spades, hearts, and diamonds, and we have here are all of our keys and the values that go with them that we want to sort. And so we're going to start by counting everything. So what do we do? Well, we say, okay, there's 3 clubs, 2 spades, 4 hearts, and 3 diamonds. How do we do that? Well, we just iterate through this thing, incrementing counts. So that's something you should feel comfortable. Maybe if you had to write code to do this, that should seem like a natural task. Now the next thing I'm going to do is I'm going to create what I'll call a starting points array, which is just the cumulative sum of the counts array. So for example, this says that the first heart is going to go in position 5. That's the problem you just did. By similar logic, the first spade will go in position 3, the first diamond in position 9, and the first club will be in position 0, because they're the smallest. Okay, so here's our starting points. And then I'm going to create another array, which will be my sorted array. And I'm going to start with Lauren. Where does Lauren go? Well, Lauren is a spade, so we see that spades are position 3. So we're going to put Lauren in position 3 and increment this to 4. So I've changed this number to 4 because we know that the next spade, JS, is ultimately going to go here. Okay, so next up, we got to process Delbert, who has heart. Okay, where does heart go? Oh, it goes in position 5. There we go. Okay, and so we increment this 5 to be 6. Next comes Glazer, who's a diamond. Okay, well, diamonds, they're going to go in position 9 next. And so here's Glazer. Next up comes Edith, who goes in position 0, and so forth. So at this point, we just happen to have done 1 club, 1 heart, 1 spade, and 1 diamond. And so the starting points have all increased by 1 since we started. Next up comes JS. So JS is a spade, so JS will go in position 4. And then we notice that JS, after he has been added to this sorted array, that this spade value is now 5. Now that seems maybe a little scary because maybe Delbert could get overwritten. That is, if another spade comes along, it's going to go right here, right on top of where Delbert lives. But of course, there are no more spades. And if you think about it, that's a pretty natural invariant, that after the last, say, spade has been copied, its starting points value will never be used again. Okay? So, continuing along, we have Sandra goes in position 10, and so forth. And one thing I want to note is notice that the sorted array is being filled in kind of haphazardly. Things are jumping in here and there, and we're always going to iterate through the original array in its original order. So just be aware that when you're working on these problems, or if you try and implement this, make sure you're not trying to fill in the sorted array starting from position 0, then 1, then 2, then 3 in the sorted array. You're going to be iterating over the original array. It's more natural, and if you'd like to see why that is, try doing it the other way. Think through it, and you'll realize that that will be slower, ultimately. Okay, so next comes Dave, who will go in position 8. then Behrman, who will go in position 2, and then finally Lisa will go in position 11, and we're done. We have now sorted all of our items, which were non-numeric and not even unique, but here we see that everything is in sorted order. Great, we did it. We have counting sorted things. Okay. So in the next video, we'll talk about the runtime of counting sort, but hopefully the mechanics of sorting, of counting sort work. And the bottom line is you can use this to sort in objects and data in time. Now it seems a little funny that we're going to do counting sort runtime next, since I already just said it, but we'll see there's a little bit more subtleties to it than what we've seen so far.